Okay, so at this point, you're probably thinking that this valid computation history business is very abstract. And so let's make things a bit more concrete with an example. So I have this example here of a Turing machine, which we actually saw during lecture 18. So this Turing machine was actually a very sophisticated way of accepting a regular language. So this Turing machine accepted the language A or B star, and looped on every string that started with a B. And the only string that it rejected was the empty string. Okay. So what is an example of a valid computation history string which represents a running of M on a certain string X? Okay, so for instance, if this is our Turing machine M, and our input string X is, let's say in this case, ABB, then a valid computation history for M on X is the string that represents the sequence of instantaneous configurations of M running on X. Right? So we need the starting instantaneous configuration. So that's, the dash, the start state Q0, and then the input string ABB, and then a blank to represent the infinite sequence of blanks right after, and then a hash, right? So the hash is the separator token. Okay, so this is alpha 0. This is alpha 0. And then what I need to do is I need to write down alpha 1. I need to write down alpha 1. But according to the rules of valid computation history, in particular according to this rule here, I need to write down alpha 1 such that it respects the rules of the transition function of M. Right? So what is M going to do if it's at state Q0 and it's reading an A? So if M is at state Q0 and it's reading an A, then it'll write an A and it'll move its pointer to the right. Okay? And it'll end up in state QA. So the way we represent that is we have the same dash, but now the pointer moves to the right here. And so it moves to the right of A, and A doesn't get overwritten, so it stays the same. And now we're in state QA, because that's the state here. And then to the right, we have the letters B, B. Okay, then we have our blank, and then we have the hash. Okay, so this is alpha 1. Right? This is alpha 1. And this is a halting configuration, right? Because it contains, so this contains the accept state, which means that this is an accepting instantaneous configuration, which means that alpha 1 really is also alpha n, right? And so in this case, the string that represents the computation history of M running on X in a valid manner is this string, right? So it's a finite string. So alpha, you could say alpha of M running on X in this case is equal to this. Okay? Okay, so that's nice. That's when you give the Turing machine, in this particular case, this Turing machine that I wrote down, the string ABB. But what happens when we give the Turing machine a string on which it loops, right? Well, let's see. If you remember from lecture 18, this Turing machine looped forever when it received an input string that started with B. I won't re-explain why, because I've already done that, but now let's see what happens when you give it an input string. So let's say BA, on which it'll loop, because we've already sort of analyzed it a few lectures ago. Okay, well, in this case, alpha of M and X, that's going to be, well, you first place the input string BA onto the tape. So this is the starting configuration. Right? And now you write down the next alpha based on the rules of the transition function of M, right? So in this case, what M is telling you is that if you're at Q0, right, and you're reading a B, then you move the pointer right and you go to Q1 without overwriting the B. So the B stays the same. You read and write a B. Okay, so that looks like you move your pointer to the right, and now it's at Q1. To the right of Q1, you still have A, then you have a blank, and then you have the hash, right? So this is alpha 1, and this is alpha 2. Okay. But this keeps going, right? This clearly doesn't end, because now when you're at Q1, well, when you're at Q1, your machine tells you that if you're reading an A, then you should write an A, move your pointer to the left, and go to Q2. Okay, so then if I write that, I will move my pointer left, right, and go to Q2. So I'll move my pointer back left and go to Q2. And then once I'm at Q2, then in this case, I read a B, I read a B, and I move right. So I read this B, I write a B, and then Q2 moves to the right and goes to Q1. Okay. Well, hopefully, even if you didn't remember that this was going to go in an infinite loop, you kind of see why now, because we have a repeating instantaneous configuration, right? And so we know, based on what we just did, that the next instantaneous configuration after this one will be this one, and the one after this one will be that one, and so on. And so we're in a loop, right? And so what this means that this string is infinite in some sense, right? So we have an infinite string. So the string is infinite. But when we talk about valid computation history, we're talking about finite strings, right? Valid computation histories are finite strings, right? Because that's how we've defined strings in COP330, right? And so an infinite string doesn't make sense, and it also doesn't make sense for an infinite string to be a valid computation history because of the fact that it wouldn't respect this condition, right? Because you're never actually going to get to an alpha n where the alpha n is either an accepting or a rejecting configuration, right? Because you're in a loop that never allows you to get to either an accept or reject, right? And so this is not a valid computation history. So that means that if this is 1 and this is 2, so that means that 2 is not a valid computation history. And this observation will be extremely important in the next video when we discuss the language containing all of the strings representing valid computation histories of a particular Turing machine running on a particular string.